And so we're going to work on the next lesson, which is about what's called DeMoivre's theorem. Nice French name. And DeMoivre's theorem extends what we learned about multiplication and division of complex numbers in polar form. So what we want to do is we want to raise to powers, right? And then also find roots. And DeMoivre's theorem helps us do that for complex numbers. And this is an extension of what we do in real numbers. We learn how to add, subtract, multiply, and divide real numbers. And then we learn how to take them to powers and then find roots, square roots, etc. Thank you. All right, let's work on that right now. So in order to do powers, that's the easy one. Let's just notice something. Suppose we square a complex number, all right? Well, and suppose that complex number has a modulus equal to r, right? And then has an angle equal to the inverse tangent of b over a, given that z is equal to a plus bi. If that's the case, then z squared will just be equal to r cosine theta plus I sine theta times r cosine theta plus I sine theta. All right, which basically means we get r squared, and since it's z times z, we just add the angles. That's what we learned last time. So we get cosine of theta plus theta, or 2 theta, plus I sine 2 theta. All right? And so then we go, okay, well, what would z cubed be? Well, that'll be z squared times z. And so we know that z is r cosine theta plus I sine theta, and z squared is r squared cosine 2 theta plus I sine 2 theta. So if we multiply those, we're going to get r cubed, r times r squared, and then we're going to get cosine of 2 theta plus theta, which is 3 theta. And so that'll be cosine 3 theta plus I sine 3 theta. Oh, so this is starting to give me a pattern. I bet z to the fourth is going to equal r to the fourth cosine 4 theta plus I sine 4 theta. And if you guess that, then you would be correct. You could probably at this point write that z to the 10th power, any complex number to the 10th power, is the modulus to the 10th power and the cosine of 10 times whatever the angle is. And if you guess that, then you would be correct and you would understand how this works for powers. So let's do this for a quick example. So here's our example. Say we have z equals 1 plus I. And what we want to find is we want to find z to the 5th power. Okay? Now, one way you could do that is you could take 1 plus I times 1 plus I times 1 plus I times 1 plus I times 1 plus I. Multiply it by itself 5 times. But just imagine going through that. You're going to have I squareds and I cubes, I to the fourth. It's going to take you a while to multiply those all out. So doing it the way we normally would is really hard. So what we want to do is we just want to convert z to polar form. So r, which is the modulus of z, that'll be the radius in this case, is 1 squared plus 1 squared, or square root of 1 plus 1 equals square root of 2. And then theta is equal to the inverse tangent of b over a, which is 1 over 1, or the inverse tangent of 1. And since 1 plus I is a first quadrant complex number, we know this is pi over 4. So there's our angle. And so if we write the polar form, z equal to 1 plus I is equal to square root of 2 times cosine pi over 4 plus I sine pi over 4, then we can find z to the 5th, which is 1 plus I to the 5th, which is the square root of 2 to the 5th power times cosine of 5 times this angle, 5 times pi over 4, plus I sine 5 times pi over 4. And then we just simplify that. Square root of 2 to the 5th is going to be 4 times square root of 2. Go ahead and check that out. And this will just be cosine of 5 pi over 4 plus I sine of 5 pi over 4. Now, if we want to get it back into rectangular form, we just need to find the cosine and the sine of 5 pi over 4. So 4 square root of 2. Cosine of 5 pi over 4, that is in the third quadrant, so that's going to be negative square root of 2 over 2. And same for sine in the third quadrant, negative square root of 2 over 2. All right, and we can then multiply this through. Square root of 2 times square root of 2 is 2. 2 times 4 is 8, so we have negative 8 over 2, which is negative 4. And then we'll have the same thing, a negative 4 times I, so minus 4I. So if you take 1 plus I to the 5th, you will get negative 4 minus 4I. So if I want to check this on my calculator, my TI-84, I can. And the way I would check it, there's quite a bit you have to do. You have to change your mode on your calculator from real to A plus BI mode. So you'll see this as an option on your calculator. And then once you're there, you can type a complex number. So I can type 1 plus, and then where do I get the I? So it turns out the I is above the key with the decimal point, all right, which is on the bottom row of your calculator. If I put that in parentheses and then put it to the 5th power, it will actually give me negative 4 minus 4I. So this is a real quick way I can use my calculator to check to see if I'm applying the powers part of DeMoivre's theorem correctly. Now notice, DeMoivre's theorem, instead of doing this, you can do this here, which makes it much easier to do. And then you have an easy way to check on your calculator as well. So these are knowing the modes on your calculator, and it's a big deal. It's something that's really worth your while. Okay, let's move on from this, and now let's try to find roots with DeMoivre's theorem. Well, just before I find roots, I want to write out the formula. If you want to take a complex number and raise it to a power, that will equal r to the nth power, the modulus of z to the nth power, times cosine of n times theta plus I sine of n times theta. And that's what we did in the last problem, is we took 5 times whatever our theta was, in that case pi over 4, to get 5 pi over 4. Okay? All right. Now, it turns out the second part of DeMoivre's theorem is finding complex roots. And that is if you have z, all right, and then you're looking to take a root of that. So like some 1 over k power, where k is an integer. So you have z to the 1 over k power. So you're trying to get a complex number. So z to the 1/2 is like the square root of z. Z to the 1/3 is the cube root of z. Z to the 1/4 is the fourth root of z. So if you're trying to find those, you're trying to find the square roots, the cube roots, or the fourth roots, okay? Now, it turns out that we've done this a lot algebraically, right? And so let's look at a couple of regular algebra problems so we kind of know what we're going to do when we go to trig form, all right? So algebraically, where this comes up is we're trying to solve an equation like this. X cubed equals, let's say 27, all right? And we'd like to be able to solve that. And normally what we do is we take the cube root of both sides, but we actually forget the complex roots when we do that. So then what we would do is we would go and we would do this by factoring. And then we would say, oh, to factor this perfect cube, that would be x minus 3 times x squared plus 9. And then the middle term would be 3 times x, so plus 3 times x, all right? And then we would set each factor equal to 0. And here we get x equals 3, and then here we'd have to use quadratic formula, so x would equal -3 plus or minus the square root of b squared 9 minus 4 times a times c minus 36 over then 2 times a. And we would then finish solving that, -3 plus or minus square root of -27 over 2. But square root of -27 is an I. Square root of -1 times the square root of 27, which is 3 square root of 3. So we get -3 plus or minus I times 3 square root of 3, all of that over 2. And so we'd get two solutions, -3 halves plus 3i square root of 3 over 2, and -3 halves minus 3i square root of 3 over 2. And these would be complex roots or complex solutions. So you can see we get the answer we'd get when we take the cube root of both sides, but without factoring, we don't get these answers over here. And what if the problem doesn't factor nicely to get us to an x squared or a linear term? Then we're in big trouble, and we learned that at the start of the year with polynomials. So we've come full circle. We're trying to find roots to the equations using solving techniques. So it turns out an interesting thing happens with these roots. What if you graph these solutions, okay? And so let's graph them. And so if we do x equals 3, it will be right here. And then if we do -3 halves plus 3 square root of 3i, okay? So -3 halves will be right there. And then 3 square root of 3i, let's get what that's approximately equal to. So 3 times the square root of 3 divided by 2, that's approximately equal, this one here, oh, this is 2.6 approximately. So then we have negative 1.5 and 2.6. So that's about 1.1, which will be right about here. So this will go, we'll go negative 3 halves. Oh, and then we go, then we go 2.6. I apologize. Then we just go 2.6 up for the I. So that'll be approximately right here. And then the other one will go negative 3 halves and about 2.6 down. So it will be right here. Now, if you mark the modulus of each one of these, this is very interesting. If you look at that, they are exactly 1/3 of the circle. In other words, the angle's 120 degrees, or in radians, 2 pi over 3, and you're moving 120 degrees each time, so this will be 240 or 4 pi over 3, all right? And so that is very interesting characteristic of these roots when you graph them on the complex plane, is they have a symmetry. So for instance, if you went for a fourth root of something, your roots might show up like this, all 90 degrees apart. Boom, 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 1, 2, 3, 4. Or it could be here, 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 and here, depending on the equation. Or it could be here and then here, but they'll all make a 90-degree angle with each other, all right? And so this becomes a really fascinating thing when we want to find roots. So we're thinking, gosh, why is there a way we can use this symmetry instead of doing all this algebra on the left? And that's really the idea. So we want to come back and we want to find all the cube roots of 27, all the complex cube roots of 27. And how are we going to do that? And that's what's the next slide. So here we are on the next slide. And here is the way we find complex roots, okay? So I'm going to call this find complex roots. And the example I gave you, I could do algebraically, but there are lots of them I can't do algebraically that I can do quite easily with the trig form of a complex number. So here's what the complex roots are. Z of k, and I'll tell you what that means in a minute, is equal to the nth root of r times cosine of theta sub 0 over n plus 2k pi over n plus I sine theta sub 0 over n plus 2k pi over n. All right? And this then is our complex roots. Now, if you'll remember when we talked about we had all real solutions, you remember we'd add 2 pi over n to our answer, and that's what we're doing here. And what's the k doing now? The k is the correct multiplier for whichever root it is. So if k is 1, that's the first root. If it's 2, that's the second root. If it's 3, that's the third root. 4, the fourth root, etc. And then the n is just whatever the root is. And so the k will tell us which root. So if you were doing, let's say you were doing cube roots, okay? Cube roots of a number, then you would have z sub 1, z sub 2, and z sub 3. And in each case, it'd be the nth root of r, or excuse me, the cube root of r, because we're doing cube roots, okay? So in each case, it'd be the cube root of r of the modulus times, then you would have cosine of whatever the particular angle was over n, which would be 3 in this case, because we're doing cube roots, plus then 2 pi over 3. So we're going to go 120 degrees, or 2 pi over 3 between each solution, because we have 3 solutions in the circle. All right? And then we're going to take whatever the angle is, and we're going to divide it by 3. And so, and that'll be the same here. So theta over 3 plus 2 pi over 3. Okay? Now, on z sub 2, how's it changed? Well, the second root will still be theta over 3, but now you'll have 4 pi over 3, because you take, k is 2, so you take 2 times 2 pi over the 3. And then that'll be the next 120 degree rotation. And so it shows that at least in complex numbers, these things are much more closely related to rotations and the geometry of complex numbers than they are otherwise. So then theta over 3, still cube root, plus, then it'll be 2 times 2 pi, 2 times 3 times pi, which will be 6 pi over 3. And so you see how you're 2 pi over 3, 4 pi over 3, 6 pi over 3. You just work through, it's a pattern every time, and that's how you would set it up. So now I've written that out. So now let's go to the problem we were doing. We wanted to find the cube roots, the complex cube roots at 27. This is the one we did algebraically. So I can take this then and I want to be able to find the R value. I want to be able to do that. So what I'm doing is I'm saying z equals the cube root of 27. So I want all the complex cube roots of 27, okay? And so let's work through that. So I first want to get R. So essentially this cube root of 27, so the complex number we're talking about is 27. So I'm sorry, this is from the equation here, but what we're saying is z is 27 plus 0i, okay? And then we're going to take the cube roots of this. We want to figure it out. And so the r is going to be the square root of 27 squared plus 0 squared, which is just 27, okay? And then the theta in this case, theta is equal to the inverse tangent of 0 over 27, or just the inverse tangent of 0, and that means theta is equal to 0 degrees, all right, or 0 radians, whichever one. I'll do radians, okay? All right, and so now we can plug it in to these three things we've written. This is the general form. I've showed you how to rewrite it for cube roots. And then now I can find the 3 roots. So z sub 1 is equal to the cube root of 27, because that was r, times cosine of 0 over 3 plus then 2 pi over 3 plus I sine 0 over 3 plus 2 pi over 3. All right, and that's equal to the cube root of 27 and cosine of 2 pi over 3, okay, is going to be negative 1/2, because this is just 0 right here, so it disappears. And so it's just cosine of 2 pi over 3 plus I, and then sine of 2 pi over 3, again, that part disappears. Sine of 2 pi over 3 is square root of 3 over 2 times square root of 3 over 2. And so if you multiply that out, the cube root of 27 is 3, so you get 3 times negative 1/2, which is negative 3/2, plus I times 3 square root of 3 over 2. Hey, that was one of the solutions we got. So then z sub 2, that's going to be the cube root of 27 times cosine of, so our angle is still 0, so it's 0 over 3, but now it's plus 4 pi over 3 plus I sine 0 over 3 plus 4 pi over 3. So now we're in the second situation right here, okay? And then I can calculate that. So that'll be 3 times, this is 0, so cosine of 4 pi over 3 is in the third quadrant, still negative 1/2, plus I sine of negative square root of 3 over 2, or it'd just be I times negative square root of 3 over 2, because sine of 4 pi over 3 is that. And that is equal to negative 3/2 minus I 3 square root of 3 over 2. And that was another solution I had. And so now we'll get the third one. So then we do z3. That'll be the cube root of 27. Notice how I've started with this, wrote these out here for cube roots. Now I'm doing this third one down here, okay? And so this will be cosine of 0 over 3 plus 6 pi over 3, which is just 2 pi, if you wish, plus I sine 0 over 3 plus 6 pi over 3 is 2 pi, okay? And now this is 3, cube root of 27 is 3. The cosine of 2 pi is 1. And the sine of 2 pi is 0. So you get 1 plus 0 I times 3, which is equal to 3 plus 0 I, or just 3. And there you have the same 3 solutions that we got on the previous page. Now, surprisingly, once you get used to the trig form of doing this, this becomes pretty easy to get particular answers. Just saying, even when you have an angle that you have to use a calculator to figure out what the cosine of the angle is, even if it's not a special angle, okay? So that showed us how to get the same answers. So now I'd like to do this for another complex number. Let's go to a new slide. Okay, so let's find the complex fourth roots of the square root of 3 minus I. So the first thing I'm going to do is I want to get the polar form of this. So I'm going to write what the modulus of z is, this is z right here. So that's r equal the square root of the square root of 3 squared plus a negative 1 squared, which is equal to the square root of 3 plus 1, which is square root of 4, which is 2, okay? And then I want theta. Theta is equal to the inverse tangent of negative 1 over the square root of 3. And so I know this angle is in the fourth quadrant, and we've done this before. This one's negative pi over 6. Theta is negative pi over 6. So there's my angles. I've done everything I need. So the polar form, so I take square root of 3 minus I is equal to R2 times cosine negative pi over 6 plus I sine of negative pi over 6. Okay? So now I have the polar form, and I have r and theta. Now, then I'm going to write DeMoivre's theorem down here. So I'll switch color, because now I want to work on finding the fourth roots. So z sub k is equal to the nth root of r times cosine theta sub 0 over n plus 2k pi over n plus I sine of the same thing, theta sub 0 over n plus 2k pi over n. Okay? So that's the theorem. That's DeMoivre's theorem, how to find the roots. Now, since we want fourth roots, that means we're going to have to find, so let me shrink this a little, move it up. That means we're going to have to find a z sub 1, a z sub 2, a z sub 3, and a z sub 4. Okay? And I already know r. Okay, r is 2. So this is going to be the fourth root of 2 in every case. So I just write that down, okay? Then the next thing then that I have is I'm going to have cosine. And so what's the original angle? Well, the original angle is theta is negative pi over 6. So I'm going to have cosine of negative pi over 6 divided by 4, which is negative pi over 24, okay? And then I'm going to add to that, now the k is 1, so this will be 2 pi over 4. So 2 pi over 4 is actually pi over 2, okay? And then plus I sine of negative pi over 24 plus pi over 2, okay? And we can write what those are going to be, okay? And then the next one is going to be the cosine. And again, we'll get negative pi over 24 here. But then it'll be, then I'm looking at it here, right here, 2 times 2 pi. So that'll be 4 pi over 4, which is just pi, all right? So plus pi plus I sine negative pi over 24 plus pi, okay? And the next one, the cosine of negative pi over 24. Negative pi over 6 over 4, same thing every time, all right? Plus, and now we're going to get 3 pi over 4, or 3 pi over 2. Notice how we're adding pi over 2 each time when we make the k3 in that case. Plus I sine negative pi over 24 plus 3 pi over 2. And then cosine negative pi over 24 plus then 2 pi. Add another pi over 2 in this case. And there are your answers right there. Now, I can compute those out. I can multiply those out and go a little further, but I do have the answers right there. Okay? Now, what's happening here? Just geometrically, we're at the negative pi over 24, and then we're adding 90 degrees each time. Boom. And there's where our solutions will be. And pardon me. You could actually take these and add them together to make them look a little more simple. Let me do the first one for you. Z1 equals the 4th root of 2 times. Then you have cosine of negative pi over 24 plus pi over 2, which is 12 pi over 24. So you'd put a cosine of 11 pi over 24 plus I sine 11 pi over 24. And you could, at this point, then figure out what this is by using a calculator. So I am going to take 2 to the 1/4 power. All right. I'm going to multiply that by cosine of 11 pi divided by 24. You got to pay attention to your parentheses here for everything. And so I'll figure that part out, and that is 0.155 approximately, and then plus the next part, which would be 2 to the 1/4 power sine of 11 pi divided by 24. And I multiply that, and that'd be plus 1.179i. Okay, and so you could get those as well as you work your way around. You could also figure it out in rectangular form from the polar form, or you could leave it in the polar form. Kind of depends what the question asks. And you can continue on doing the rest of these. I've just done the first one, but you can continue on and do the rest of them. Okay? And get a numerical value. All right, let's go to the next slide. So that's it. That's how you do it. Just as a reminder, these are the two parts. If you're going to raise to powers, you're going to use complex number to the nth power is r to the n times cosine n theta plus I sine n theta. All right? And if you're going to do a root, you're going to do the kth root, basically, is equal to the nth root, whatever your nth root is of the modulus, times cosine of your polar form angle theta divided by n plus 2 pi k over n plus I sine of the same thing, theta sub 0 over n plus 2 pi k over n. And that then, these are the two parts to DeMoivre's theorem which help you do powers and roots. And surprisingly, it makes doing things easier, all right? Relatively speaking, but it's better than going the long way around with your by hand calculations algebraically. Now, you can use a calculator to check this pretty easily, and you can sort of check this. That's why I haven't done it on a calculator. Alrighty, talk to you later.